They say it's in an email. So let's do a quick review, just to make sure we're all on the same page. Is that we've been dealing now since the midterm with purely in the complex plane, right, with H of S. And so since everything we do is linear, these are going to both be polynomials, right? We have the numerator polynomial and the denominator polynomial. And the numerator polynomial controls what kind of filter or what the name of the system would be, right? So we could have a high pass filter where you have S squared, or S cubed. Right? You can have a low pass, you have omega naught squared, omega naught cubed. A band pass, you must have an even number of poles. And you have notch where you have both the high and the low summed together. And then the denominator sets if the system is in control or not, right? If all your poles, the real part, are less than 0, you're in control, right? And if you're a second order system, then you can have a special name, over critically or under damped, right? If you're higher than a second order system, you really just have, you just call it what it is. You have complex poles, repeated poles, or different real poles, right? So in a third order Butterworth low pass filter, you would have a pair of complex poles plus one real pole. Now, if the poles, the real part is 0, there's two options. If the imaginary part is equal to 0 as well, then you have an integrator. And you have an oscillator if there's some non-zero component, right? And if a real part of your pole is greater than 0, well, then you're going to have some kind of exponential increase. Now, what about when we put something into a feedback network? All right, this equation Q of S is assuming this particular type of feedback network, where you have a summer, the input comes in on the positive side, you have the transfer function of the original system, and then that is fed back through G of S and subtracted. When you do that, you get this equation, right, which we've done several times, all right? But I think it'll be helpful to actually substitute the numerator and denominator polynomials in for H of S. So wherever H of S is, we're going to substitute the numerator and the denominator, right? So H of S, we multiply the denominator through, right? The denominator times 1 is just the denominator. Then the denominator times G of S times the numerator divided by the denominator. Well, the denominators cancel, right? So the denominator of the old function becomes the new denominator. Excuse me, the denominator of the old one is there because you multiply it by 1. That's the one that's not in control. The numerator is now also in the denominator multiplied by G of S. This is what you manipulate And really, the only thing you have a choice of is this G of S. What do you, you have to choose a transfer function and then come up with some conditions that will keep all the poles on the left-hand side. It's right there. Now, the old numerator, we scale it by G of S, and we have to select this function to get all the poles on the left-hand side. Now, what are we going for in a way that's easy to remember, right? Is every sign of each term in the polynomial, in the new polynomial, has to have the same sign. So everything has to be plus or everything has to be minus. And there can be no missing polynomials of S. So if it's to the cubes, you have to have S something times S cubed plus something times S squared plus something times S plus something not times S, or what I just said, but everything with a minus sign, right? Now, the old numerator is replicated right there. So whatever the system was, or what I should say is, the old system was out of control. So it's either an integrator, an oscillator, or has exponential control. But what I'm trying to say is that whatever the system becomes, right, in control, that numerator will give you a hint of what's going to happen. So if it's a constant, no term of S, it's going to be some kind of low passish type function. If it has, an S term, and of course it depends, right? So let's do an example, right? You can have a transfer function A divided by S minus B. Now you can have this in a physical system, but even in our DF2 circuit, if we wired something in on the wrong side, you could get this to happen. Now, the solution, of course, is to wire it in on the proper side rather than make a whole new control system, all right? But, right, if B is a real number and is greater than 0, I take the inverse Laplace of that, I'm going to get an exponential increase. So that's the problem that we need to solve. And that should be N of S indicates. So let's multiply it through. Here's our original H of S. Here's our transfer function that we're going to put it into, multiply it through. And so here's our original denominator that would have been out of control. The old numerator is there plus G of S. So we've done this, but really, what's the problem we need to fix? You can shout it out or put it in the chat.
We can't have negatives?
You're getting there. And I see your response, Andre. But what you're trying to say, Andre, though, is you want the pole less than 0. What's the problem here that we're trying to solve? You're kind of talking about the solution. And if everything were negative, that'd be fine. If this was minus S times minus B, it'd work out. Okay, yeah, Osman, that is a solution. Nick, not quite sure what to say. Maybe I'll just remind everybody that I do have office hours Monday, Tuesday, and Wednesday. Now, the thing about oscillations, right, is you have to have the real part equal to 0, and you have to have a complex number, plus or minus, a complex conjugate. The only way you can have that is with a second order system. And so S is not second order, so it can't be oscillations, right? So Osmond, you're solving the problem. I don't know, I've sent it out a lot, all right? Send me an email later, okay? I gotta keep trucking here. So what's the problem that we're trying to solve here? What's wrong? Right, Dave, you got it. This will be on the right-hand side, which gives exponential decay. Right, Donald, yeah, they're not the same sign. When I say they're not the same sign or there's a missing term, that is like a shorthand, right? It is what's wrong and it's what we'll use to mathematically fix it. But in this case, it's really, we have exponential increase because they're not the same side. That's why let's just take a moment there, right? So if I were to plot this, right, when S equals B, right, H of S goes to infinity, right? So that's B. But now, they're the same side, right? So minus S minus B equals 0, right? And now we have S equals minus B. Sure, it's inverting, right? Okay, so all of control theory is dependent upon the S plane, right? We have the real axis and the imaginary axis. So them having opposite signs is what puts B on the positive side, which then the inverse Laplace of this is proportional e to the plus bt, which is exponential increase, right? So the problem is this term is negative and we want it to be positive. So we want this to be greater than 0. All right, what can make that happen? Right? Wait. Oh. This is what we want. All right. So I'll just throw out some possible G of S's. One is K, where we just multiply it by something. Another one could be K times S, which is a derivative type feedback function. And one could be K divided by S, which is an integrative type feedback function. So which one do you think will, when you multiply it by a constant, can be used to make this whole term greater than 0? Yeah, right, Osman. K is just like a gain. It's just a number. Okay. Good question. Right. So let's write that out. So you have minus b plus ka, right? And we're saying our feedback function is just proportional, right? Well, if k times a is greater than b, right, this whole term, right, if that's so, then that means if this is greater than 0, that means we are now here. The new pole is here. The old pole, and I've drawn them symmetrically, but I just have to get it. Yeah. So we started here and we kept multiplying, changing k until we got over here. Now, let's just see let's just try a few more though, just to show. What if we had selected k times s, right? That's proportional times that s, right? It's just makes things a derivative. When you take the inverse Laplace of that, it takes a derivative. So let's find our new transfer function. We have a s minus b plus ks a. Well, this is a function of k, a function of s, and so is this. So really, we get a 1 plus k sa minus b. Now, if you notice, it didn't add in something over here. Oops, thanks. right? It's just made another S term. Now, yeah, in general, I think people like to keep the constants positive, right? But if Ka were less than 0, right? Meaning it's starting to get negative. Right? If this whole term was less than -1, then we'd get a minus sign here. The minus signs would all be the same. Yeah, for that example, yes, Marielle, I would say so. Because later on, you'll see that there's you have all these terms, and anything that changes the denominator will change where the poles are. Yeah, so that's very correct. So there is a way to, if you allow K to be negative, to get this to be in control.
Could you do the other GMS as well?
Sure. Let's do integrative. Okay. So now I don't have my orders of polynomial, in a way that I can rapidly see what's going on. So let me multiply, in this case, through by S's, right? Now, yeah, in this particular example, now I've changed what this is going to do, and I have S squared minus BS plus KA. And so I can make this positive, or I can make this negative to match this sign, but this is still positive. So I'm not going to be able to do it with this. With integrated feedback. And the best answer would be to use the simplest kind of feedback, right? You can do proportional just with a ratio of 2 resistors. If you wanted to do a derivative, you'd need another op-amp circuit or something taking the derivative in the feedback path. Okay. Now, these are just other ones that we basically found our answer here. That's the simplest way to solve it, right? Well, Matthew, K fixes it, right? And it fixes it in the simplest way possible, right? and I don't need an inversion. So if I had KS, I need to have an inverter, which, you know, this circuit right here is transfer function is this. So it inverts and we have an S. So this, if I put this in the feedback loop instead of, you know, just two resistors, right? I could get it to work. But this is more complicated than just setting two resistors, right? But in, you know, I would have had to ask the question, find the simplest way to fix this being out of control. Then proportional would have been the best answer and the only answer. But if I said, can this circuit, you know, or make this transfer function in control, and you used KS and then came up with the right conditions, it's right. And it should be marked as right. No, I might forget that, and then you just have to tell me. I know it might not seem that I'm trying to keep things simple, but in general, it's the way to go. All right. So now let's go on a test. You know, I think in life, why use something that uses a lot of parts, right? You know, if I have a circuit that is equivalently fixes a problem for fewer parts, then I'm going to use the fewer parts. Now, sometimes extra things are added because you're actually fixing a problem. You can't just disconnect things. All right. And so I'm just going to tell you a little story. Case in point is old television sets were completely analog, and to move the CRT back and forth, right, and right on the phosphorus like you see me doing here, right, were analog control systems, which were really transistors with resistors. Now, you know how we're talking about the use of feedback actually makes the op amp easy to use. And so there was this TV manufacturer, and resistors, I guess, were expensive. And what this person would do was go around into an engineered circuit and start cutting resistors. And if the TV kept working, he'd say, we don't need this resistor. Hey, Matt, are you from the military, Matt? Because that's where I used learn the KISS principle. And what it turned out is, yeah, if everything was tweaked right, you didn't need that resistor. But as soon as things aged, things would get out of whack, and you'd have to call the TV repair person to come over and fiddle with something to get it back in sync. And then as it would get old or humid or whatever, or hot, it would get back out of sync. So cutting just a simple resistor out of it spawned a whole TV repair business. Oh, okay. So it doesn't have to be the military. All right. Anyway. Oh, sorry. Back to the integrator. Oh, sorry. Keep it simple, stupid is what KISS stands for. Sorry. Nobody's stupid in this room, virtual room, just so you know. So in fact, So in fact, it's an integrator. All right, D of S says that it'll be like a low pass thing because it's just a constant. We push everything through. Okay. So again, you know, what is wrong? Well, you could set the wrong value of GS, right? What if I put minus K? Oh, well, then I'd have a pole in the wrong spot. But really, all I have to do, G of S just has to be some constant greater than 0, and then this pole will be on the proper side, right? So I'm just going to grab that. So we could have G of S equal to K. All right, let's do it. A S plus KA. Well, all I need is KA greater than 0, right? And I will get my low pass type function, right? It'll be in control. Now the larger K, so before I was here, and now I'm moving it here, and the larger K, I keep moving it out. And so if they said bring it in control, and I want a pole at 100, right? Let's say A equal to 1,000. And you say, I want my new pole to be, I want the pole to be on the left-hand side, and I want it to be minus 100, right? Well, then I would set KA equal to, well, actually, I would just do that, because I know it's going to go on the proper side. So in this case, K would be 1/10, right? And would put the pole exactly where I wanted it. Hold on. Looks like there's a lot of good comments here. No, Francisco, nobody is stupid. Right. So N of S indicates what kind of system when it's in control, kind of what system it will be. Okay. So in this case, N of S was A. The original N of S is A. So that's going to be some kind of low Paschus type thing. Okay. So now we have H of S equals S times A. So S times A will, if this were in control, right, if all the poles are on the left-hand side, this would be a high pass filter, right? But we have a slightly different numerator. So we multiply all that through. So the fact that it's will be a high pass isn't the issue. It's just, if I write this out, I'll have S minus B nope, that's a positive. There's a minus B plus this. All right, so I'm sorry. All right, I have the 1, then I have plus G of S times A minus B, right? I'd want to make these the same sign. So one option, right, is G of S equals K. Right, and if I make that less than 0, then the sign is negative, and then I have, I can get it in control that way. Although I will have inverted it. Because now this will be minus, that'll be minus. I can pull out the -1 and multiply the whole thing by -1. So yeah, proportional even works in this case. What other things will fix it? Well, these are of opposite signs. Proportional allowed me to change the sign of the S term, but what will allow me to change the sign of the constant term? So I see an S here. If I want to combine that with B, I have to get rid of it. So G of S equaling K divided by S, this would result in K divided by S times S A. Those would cancel, right? I would be left with and as long as K times whatever A was greater than B, then this would be on the left-hand side. And so, yeah, integrative would work, but it seems that proportional works as well, right? So what if G of S equaled K times S? All right, let's put it in there. So now I've made it second order, right? So I have S squared. Okay, that's good. I have S, that's good. I don't have S, but I have a minus sign here. And you'll say, well, I'll make this negative. I'll make K minus 1. So that'll be minus. That'll be minus. But I don't have a way to make that minus. So I really can't do it that way. Okay? That's a hard no. And really, so in either one of these, right, I'm either changing a minus, I'm either changing the sign of this or I'm changing the sign of that, right? But other times I'm adding something. All right, so if this was my old N of S, right, and I had S squared plus 1 G of S NS, what can I multiply by N of S to get that missing term, right? And you might have to do more than one thing, right? Because if I had this, I had S squared, something missing minus 1, there's two issues. I got to turn this positive, and I have to add in a term. So, and it all depends. If N of S was a constant, or N of S had some kind of derivative, this is second order, it could have something S squared, and it could even be notch-like. So you have these kinds of choices, and then you have things that you can multiply through by to change it to what you need to happen. And so on a second order system, right, I could have let's say this is my original out of control function, right? What could be wrong with it? A1 could be negative, rest positive. A2 could be negative, rest positive. A1 missing, A2 less than 0. A2 missing, A1 less than 0. A1 and A2 missing. So that's 1, 2, 3, 4, 5 combinations, right? For 4 possible numerators, right? So that's 20 possible combinations just for a second order circuit, okay? So if someone were to write a random test generator, they might be doing that. Now, what I was trying to do here is abstract everything as of what could be the possible problems, right? The possible problems for a second order system are something's negative, right? What, you know, and actually both could be negative. Did I put that? Yeah, nope. That's a fifth option. So these are all the things that could go wrong. And you would have possible numerators, right? And then you could have possible G of S's to fix it. And so I can give a few examples, but I mean, it's true. I could have SA plus B, and that's a real system. It's just not a filter, right? And I guess you could also have S squared plus S. They're not named filters, but they are proper. They're possible systems. So these are all kind of the possible existing second order numerators, right? And I think these are all the possible ways it could go wrong, right? Oh, there is, the way I've done it, right, is there's nothing scaling the S squared. So I can't really make that negative. But does everyone see any trouble with me saying, you know, here's, for a second order system, this is really all I could ask, because it has to be wrong to be fixed. What if A1 is missing? A1 is missing. Right, Vicente? I mean, I think I had that. A1 missing, A2. Did I not put that? My bad. A1 missing, regardless. A2 missing. And I guess to make it complete, I guess that's 8. So what are the possible problems? S squared can't be missing. Otherwise, it's not a second order system. Okay. So what are the possible ways, you know, everything is there cases, right? A1 less than 0, A2 greater than 0, A2 less than 0, A1 greater than 0, and then A1 and A2 are less than 0. Missing. A1. So if A1 and A2 are missing, that's just a double integrator, right? If A1 is missing, right, A2 could be greater than 0, A1 can be greater than 0. let's just, you're going to get S squared plus or minus A2. And that will be complex. No. I have to do the quadratic equation. So minus 4. So if A2 is greater than 0, it becomes an oscillator because it's plus or minus an imaginary number. If A2 is less than 0, this is positive, and you get one pole here and one pole there, and you get exponential increase. I say A1 is missing, right? So A2, oops, I meant A2. Thanks, Matthew. So for a second order system, whether you're going to get an integrator or an oscillator or exponential increase, this will tell you. Now for a third order, right, well, then you need the cubic equation, and then it gets more difficult from there, which is a little bit more than I would expect on an exam. Okay. But, all right, what if, I'm just going to take it to the fourth. Right. Any of these A's are less than 0, it'll be out of control, right? So if any one of these is less than 0, even if 2 are, even if 3, even if 4, right? It'll be out of control. If anything is missing, it'll be out of control. Now, yeah, if all of them are missing, it's something divided by S to the fourth. That's a the fourth integral. Okay. So let's say this is missing. Let's say this was our original numerator, right? Well, then we have G of S times B. Well, it's the constant terms that's missing. So all it has to do is be K times B. K just has to be greater than 0, and we'll have a term here, right? What if we had this, right? We have a missing squared, right? So we have G of S times the old numerator. Oh, wait a second. S squared is already there. We just need to have K be S squared and then make sure that this is greater than 1, and it's fine. Now, sure, what if we had just this, B? Then we would get rid of that. We need a S squared term, right? So our feedback has to be G of S, some constant, S squared, which then will fit right there. Okay? So you just look at the thing you need and make GS, multiply it and make that happen. Okay? So my old questions used to be, will this kind of feedback make this in control? Now, yep, Alex, you're right. Now I tend to ask the questions, this system is out of control, find a G of S to fix it. Okay? No, not yet, Matthew. And I have a few typos to fix. So, I want to fix the typos before I post it. So here it's easy to see that one of the poles is 0 and we'll have some kind of integrator function. But a lot of times you'll see this as s squared plus sb, and this is the missing term. So in order to get that it's at 0, well, you just convert it back. And now you can see that integrator type, pole at 0. All right. But when I'm fixing a problem, I like to leave it out like that. The old numerator is the new numerator. I'm going to write that out. The old denominator is multiplied by 1, so it's still there. The old numerator is multiplied by the feedback function, right? And you can see we've already done this one. Is what's missing is the constant. So G of S equals K, right? I have all the terms. The only thing left is to make sure that this is positive. So I make K greater than 0. So if you look at last week's slides and videos, right, it's done more thoroughly, okay? But it can take a few times to really get this, right? And so if I have a pole here, right, that means H of S is something divided by S, right? And when we have something, when the system is something divided by S, right, you have an integrator, right? And so what if the input is a step times the system, right? 1 over S squared, the inverse Laplace of 1 over S squared, RT, right? It goes on forever, right? So that system is out of control. If I have one complex pole, I got to have another. There's no way around it because you have the square root. So in that case, we could have this, right? So the inverse Laplace of this will be, it's there's more to it, but you have a sine wave there, right? And think about it, things that decay to 0 are decaying to 0 because they're dissipating power. Complex systems that are purely complex, they rearrange power, they store power, they hold it, they deliver it, but they don't dissipate it. So it can oscillate forever. All right. And then over here, right, that's, that's B. We have exponential increase. Now, sure, I can have 2 of them there. I can have complex, but it doesn't really matter. You've got exponential growth. Okay. So if you have a system like this, you got to figure out a G of S to move it over here, right? If you have this kind of system, you got to move it here. If you have this, same thing. Now, you just don't move them in a straight line. There's actually kind of complicated arcs. If this is really your thing, EE 132. And this is just a very simple way of looking at it, okay? I don't mean to, I'm not trying to make anybody feel bad. But this is just the basics so that when you go into 132, you understand, you can start understanding the conversation, right? But really, a lot of what we're talking about is robotics. For example, now this is done in detail in the book. All right. So this is a transfer function of an inverted pendulum that has a certain length and gravity is that value. How they come up with this isn't really a linear problem, but if the angle is small enough, you can use the first term of the Taylor expansion of sine and it becomes linear. All right. So really, this sign is minus, and if you recall, that gave us a S squared means we're going to have two poles. When it was plus, it turned out to be an oscillator, but when it was minus, you had one pole here, and you had one pole here. And think about it. If I knock this, and this starts to tip over, gravity makes it start that angle getting bigger, makes it tip over more, makes it tip over more, makes it tip over more. And so that's a thing of positive feedback, where going in that direction makes going in that direction happen all the much faster. All right. So we can see not only do we need to change this sign, but we need to add a term. Even before I get started, I know this has to be positive, and I have to add an S term. So Q of S, and notice it's going to be a high pass. And think about it. You want this angle to be 0. So if I tap it and this starts wiggling, I want it to end up back at 0. Well, right? What does a high pass do? It detects the edge, right? And then it decays back down to 0. Now it's second order. It might do this, right? And yeah, doing this, probably we don't want. So we don't want these complex poles too close to 0. All right. We have the original denominator plus G of S times the original numerator. All right. How do I turn this positive? Right? Well, I have an S squared. Well, there's more than one way to do this, but I'll just do it this way, is that I want this to be positive and come up with another term. All right, because I could come up with another term and make this negative, but so how do I get S squared divided by L into just some kind of constant? Well, that means I need G of S equaling to some K divided by S squared. Because when I multiply this out, the S squareds will cancel and I'll have K divided by L. I can make K bigger than the gravity term and that'll fix it. But also I'm missing a term. I'm missing an S. So what I need to do is add something else divided by S. So now I have K1 divided by S. The S is still there, right? So let's rewrite it out. I have S squared plus K minus G of L. And then I have so I have to make that positive. And I have to make that positive. Now, sure, I could have turned G of S just times K and made it negative. I could turn that term negative and then keep the S term, have K1 negative, and then it would have just been inverting. But it would have been an inverting. So if this was my step, it would have just turned into this. It would have gone the other way and then come back to zero. So it would have been the same. Hi, Esteban. No, I don't. I'm really a device physicist. That's really my thing. We have some excellent 132 instructors. All right, you have a choice to make, 132 or 160. 160 uses the same math we're talking about, but applies it to communication systems. 132, you can see this, it's control systems, but uses the same thing. But there's there's even other things. The term is like a Nyquist plot. That is more of a 132 term. Right, complex. So if I just have a set of complex poles here, and then I have a set here, and then I have a set here, right? This gets more and more, complex poles means you're underdamped, right? But the closer you get, the more oscillations you'll get. And really, if you're right here, right on top of it, if it takes a day for your oscillations to stop, you know, most people, that's not a good thing. Osman, the only difference is, like, I would probably want to have put two different numbers here, K1 and K2, right? It's not the same K. but it could be. Okay. Okay, Andre says if you got to go, you got to go. Right? Yes, this kind of thing, you'll get a question. Here's a system out of control, fix it. No. You guys got 112 because it's really important. Okay. I teach this course, but it's not, just so you know, right? I don't think it's the only thing you need to be doing. I'll create some things, okay? But I know you got to go. All right. Take care.
Have a good evening.
Oh, yeah. Bye.
Professor, you're still in the meeting.
Well, take care, guys.